So thank you for coming to the last part of the Southeast summer series. Summer seminar series. The last speaker is Changrim Ahn from Ewha Women's University in Seoul, and he's going to talk about Jordan blocks in integral models in Fishnet limit of twisted n=4 super-Yang theory. So please start.
Okay, thank you very much for kind invitations under this Corona situation. Today I'll explain what I'm doing recently on these Jordan blocks. So this is based on works with a collaboration with Matthias Tagodacker in Berlin, and another one which we are preparing is with Corcoran, who is Luke Corcoran, who is a student of Matthias, and Matthias me. So I mean, let me go through some briefly about the interesting feature of this ADS-CFT duality, which that basically string theory is a dual to super-Yang theory, in particular in spectral problem where conformal dimensions of general non-BPS operators in super-Yang theory, such as a single trace operator composed of all kind of quantum fields in super-Yang theory, and the corresponding string configurations moving in ADS5S5, in particular, the dimension of this BPS operator is related to the energy of those string configurations. And then recently, there are also active progress to generalize this two-point correlation function, which is a conformal dimensions, is to the 3-point function or even higher. And all this development is based on, well, integrability. So for example, in one loop, which is based on weak coupling, where lambda is a famous tubed coupling, then some perturbative calculation is generating that the conformal dilatation operator, which determines the conformal dimension, is given by certain integrable spin chains. Or in very large coupling constant, then it is described basically by classical, the world sheet theory, which is described by some classical integral systems. But more surprising is that this non-perturbative integrability, which is valid for any lambda by some exact S matrix, like this famous Beiser test matrix. Then the people were studying how we can extend this ADS-CFT system to more wider class of the quantum field theory. And the most well-known case is actually so-called gamma deformed super-Yang theory, where certain the deformation parameter, which I call Q here, is introduced. And well, in this super-Yang theory, there is this interaction term, which is pi to the 4th term, where pi is this adjoint representation field in the super-Yang theory. And this Q, well, if Q is all 1, then this is back to original super-Yang. And if all Q, there are 3, this is one IJK is an index starting from 1 to 3. So there are 3 parameters possible, but if they are all same, then this is so-called beta deformation. If they are all different, then this is called gamma deformations. And then this string dual theory has been studied based on TST transformation, and also the non-perturbative integrability based on certain deformed S matrix has been proposed. But another interesting application of this generic twisted super-Yang theory is a so-called Fishnet limit, or strong twist limit, first studied by Kazakov and his collaborators, by considering some double scaling limit where the tubed coupling goes to 0, but these deformation parameters going to infinite, such that this product lambda times qk is finite. And from the previous slide where I wrote the Lagrangian, this lambda comes together with the qk. So although lambda goes to zero limit, where such a kind of a term, first term can vanish, but second term doesn't. And this special the form of the interaction term make the Lagrangian very simple and non-trivial. So in this limit, the interacting four-dimensional Lagrangian can be described by certain these four interaction terms, four scalar field interaction terms in a joint representation, and with some specific coupling constant. And in Feynman diagram, this introduces certain vortex between these three different types of the scalar fields. And then based on this special interaction vortexes, somehow these authors found that all other Feynman diagrams can be summed because there is only one non-trivial Feynman diagrams for each order of the perturbation theory. So that's why people are although superharmonic theory itself is not exact solvable except this spectral problem. This special limit, this Fishnet limit may be really exact solvable four-dimensional quantum field theories. Now, since in this limit lambda goes to zero, actually, if I restrict this into the user spectral problem where conformal dimension is the issue, then the dilatation operator is described by spin chain Hamiltonian. And since lambda goes to zero, we don't need to worry about second loop, two loop, or three loop dilatation operator because one loop is only contributing. So user one loop spin chain model is getting important, but since due to this strange limit, the spin chain Hamiltonian still integrable has some special features. So if I consider this sector composed of three scalar fields, pi 1, pi 2, pi 3, which I call here, then the resulting the integral spin chain Hamiltonian is generated by so-called R matrices here, which is a 9×9 matrix because there are three states. So 3 to the square is 9 with some kind of a U dependence where U is a spectral parameter. R matrix is a fundamental building block in integral models, which I'm going to explain a little bit more later. Then it's natural to approach this integrable spin chain model based on algebraic variances. And first of all, one can construct usual procedure is going like that, right? That based on this R matrix, what one construct the transfer matrices, which depends on U spectral parameter. And then since R matrix satisfies Yang-Baxter equation, two transfer matrix with a different arguments like V here are commuting, and that defines infinite number of conserved charges. And then one can construct specifically Hamiltonian based on logarithmic derivative of this transfer matrix. And it looks like following that I introduced this simple notation to EIJ. This is a kind of 3×3 matrix where one first row and second column is 1 and all our other entry is 0. So using this short notation, I can write down the Hamiltonian corresponding to that Fishnet limit like this. And then second step in integrable model is to approach this algebraic variances by introducing certain commutation relations, so-called fundamental commutation relations among these monodromy matrices elements, and they should satisfy this Yang-Baxter relation. And using this kind of commutation relation, one can find all the exact the eigenvectors and eigenvalues. But it turns out that actually this algebraic variances procedure is of no use in this case because this strange form of this R matrix where more entries are 0, they are vanishing. Actually, you will see more generic R matrix soon, but this is a special limit this Fishnet limit already eliminates many elements from this R matrix, such that this commutation relation is not really commutation relation, because usually commutation relation, for example, between A and B is A and B commutator, or AB minus BA. But in this strange R matrix, this commutation relation that usually the right-hand side, for example, is vanishing. So you have only A times B type of the is 0, for example. So one cannot use the commutation relation anymore. And so one cannot continue this algebraic variances procedure. So since we cannot use this the algebraic variances method to this model, although it's integrable, it is integrable because one can construct the Yang-Baxter equation, and still the transfer matrix satisfies this commutation relation. So this spin chain model is integrable, but it's not variance solvable. So we'll go to some numerical calculations for certain size. Say here L is the size of the spin chain. So usually it's very difficult, but one small trick is that since the states belong to, since there are 3 types of the scalar fields and it's all possible permutations, if I call total number of fields as L and the total number of pi 2 and pi 3 to be M, and the number of pi 3 to be K. Of course, this pi 1, pi 2, pi 3 is can be redefined, of course, because there's no reason to choose only pi 3, for example. But anyway, if we fix these numbers, then they should be preserved by these interactions. So we can, instead of the naively considering 3 to the L by 3 to the L problem, one can fix certain sectors decided by L, M, K, these 3 integers, where L is number of total fields and M is number of pi 2 and pi 3 and K is pi 3. And the size of this transfer matrix becomes much reduced by these numbers. And then one can try to diagonalize this transfer matrix numerically. And this is the result I want to show. So for example, if I consider L to be 4, and then M to be 2 and K equal 1, then this factor, this combinatorial factor becomes 12. And then we found that actually it is non-diagonalizable. This is a result of a diagonalization, numerical diagonalization using the MATLAB. And it turns out that it's not diagonalizable, but instead they generate so-called Jordan blocks. So for example, this one has some kind of -1 as a diagonal element, but in first off diagonal, it is somehow normalized to be 1. So if this off diagonal is 0, then it's diagonalized, but it cannot be reduced to 0. So we found this Jordan block is obtained. And also interesting is that still the diagonal value becomes the root of unity, which is a fourth root of unity. So actually it's related to this L, which is a 4. So diagonal element is always L's root of unity, but this off diagonal is not 0. So they are kind of the separated by 3 by 3 blocks for each eigenvalues, which is root of unity.
Can I ask a question?
Yes, sure.
So how should I think of this physically, that a spin chain Hamiltonian is not diagonalizable? And what's its implication for the Fishnet model? Does it mean the anomalous dimension is not well defined, or?
Yes, because the this eigenvalue is always the eigenvalue is corresponding to conformal dimensions, for example, but one cannot find out the eigenvalues. So certain combination of this composite operator is not by acting this dilatation operator, they are moving to you cannot find any in any linear combination of this composite operator, you cannot find out the eigen operators. Instead, you goes to some other operators and so on. And there is only still there is one eigenvector at each. I'll talk more about this Jordan block structure, but each Jordan block, for example, is 3 by 3 here, then naturally you will expect that there should be 3 eigenvectors, right? Although it is degenerate, still you can find 3 eigenvectors. But when they generate Jordan block, you cannot find out 2 eigenvectors. You can expect only 1 eigenvector. So each Jordan block, still you can find one the eigenvector, but not all of them, not 3 of them.
Okay, so the fishnet in the large N is still a conformal field theory. So if I say take 2 conformal operators, the 2-point function, it still has a well-defined conformal dimension, right?
Right.
And usually this is identified with the eigenvalue of the Hamiltonian. Now your Hamiltonian is not diagonalizable.
Right.
So how is this relation?
Right. So actually this phenomenon has been discovered in logarithmic conformal field theory some many years. And then it is actually observed in other contexts, other conformal field theory too. So correlation function, 2-point function, for example, generates certain logarithmic dependence.
I see. So you're saying that this form is not the usual form, but logarithmic corrections. Okay.
Right.
Okay, thanks.
And the other values of the case where L is 5, for example, then this combinatorial formula is should be 20. Then again, Jordan blocks appears. But here, interestingly, so the diagonal element is a 5th root of unity. And one of them is 1, of course. Then this is a 4 by 4 Jordan blocks. But actually, if you go down to, sorry, this is a, I'm confused. Sorry. So this is a Jordan blocks with 4 by 4 size. Okay, so there are 5 of them, so it's 20. So it's the same structure as this. But if I increase the M, remember M is the number of these 2, pi 2 and pi 3, L is total field. And then some new feature appears. So instead of, there's, since eigenvalues are 5th root of unity, there are 5 such eigen diagonal elements. So if I divide the total size by 5, there are 6. So one can expect maybe the Jordan blocks is a size of 6 by 6 matrix, but it's not. Actually here is a 5 times 5 Jordan blocks with eigenvalue 1, or other 5 by 5 Jordan blocks with the other values of the 5th root of unity. But all the down to here, there's 1 by 1 matrix. So the eigenvalue 1 Jordan block is not 6, but it's a split into 5 times 5 with a plus 1 by 1. So we expect that this structure should be somehow generic. And we consider the following. So the generic structure should be following that say, since in general L, I introduce omega, which is fundamental L's root of unity. And then this 1 is when omega instead of omega is 1 to the 0th power or L's power here, and omega and so on. And if I focus on some block with omega n eigenvalue, where n can be from 0 to L minus 1, and then this has not just a single Jordan blocks, but actually it's split into many such substructures, like this L1 by L1 Jordan blocks, and then L2 by L2, and so on. Okay, so we have seen already one example in this case. The 6 by 6 is a split into 5 plus 1. So this kind of splitting can be in general. And we somehow worked a little bit more, and with well, within my desktop computer limit, I tried to diagonalize this transfer matrix for m equals 3 and k equal 1, and then and increase the L. The L equal 5 case I already explained, 5 plus 1, where this this L minus 1, L minus 2 over 2 is actually this combinatoric factor divided by L, because we can assume that the same number of the eigenvalues will appear. So since there are L's root of unity, that means that there are L different kind of diagonal elements. So if I divide this combinatoric factor by L, this is the formula. And so when L equal 5 is 6, and then I found that 5 plus 1 splitting. When L equals 6, which is 10, then we found that it is splitting into 7 plus 3. So 7 by 7 Jordan block, and 3 by 3 Jordan blocks, and so on. And then as I increase L further, then actually they show some kind of further splitting into the different Jordan blocks. And it's easy to find out some general picture, although I cannot judge numerically, but one can kind of guess that it will be something like for a given L, the largest size of Jordan block becomes 2L minus 5, then it changes by 4 until it reaches either 1 or 3, depending on the value of L. Of course, this kind of a experimental observation has a limitation, because you know, numerical diagonalization gets very difficult for higher value of M. Even 4 is difficult for me. And here so far I consider k equal 1. Remember, k is just one of this say pi 3 number of pi 3 field. But if I introduce more pi 3, then well, one cannot do much. Okay. By the way, let me briefly review about these Jordan blocks. So the Jordan block has this kind of form where eigenvalue, diagonal value is A, say, then it's a degenerate. And then the point is that this off-diagonal element is not 0. All same, one can normalize this to be 1, and all other elements are 0. This is a typical form of the Jordan blocks. And then one can find easily that if I eliminate this diagonal element by deducting by this A times identity matrix, then if I act this matrix on En means that this unit vector where nth entry is 1 and all others are 0. For example, E1 is 1 and all other elements are 0. E2 means that 0, 1 and all other elements are 0, etc. Then one can easily find out that if I act this reduced A minus small a, on En's vector, then it becomes En minus 1. So if I act A minus A times identity up to nth power, where this n, capital N is the size of this matrix, Jordan blocks, on En, then it's 0. So this would mean that if I act A minus this matrix on E1, which is 1, 0, 0, 0, then it's 0. So E1 is true eigenvector. But all other vectors are not satisfying this eigenvector relation, but instead they satisfy so-called generalized eigenvector relation. Instead, if this power is not 1, but if you take the nth power, then En behaves like eigenvector. So this En is not true eigenvector. Okay, so sometimes it's called the Jordan descendants. So each Jordan block has one true eigenvector. This is E1, but there is no further eigenvectors. That's why it's not possible to diagonalize completely. Okay, that's some basic things. So our first goal is that whether we can understand this Jordan block structure in the context of integrability. Okay, so let's consider the R matrix which generates from this one loop dilatation operator of the super Yang-Mills theory before taking this Fishnet limit. So just keep Q, okay, and we are not going to take the limit yet. Okay, so then this is well known in this early days of this ADS-CFT calculation, that it is generated by so-called SU3 R matrices, where this deformation parameter Q3, Q1, Q2, Q3 are appearing in this way. And then, of course, if I take the epsilon goes to general limit, where I introduce epsilon as a QK defined by Cauchy K over epsilon. So if epsilon goes to 0, Q goes to infinite. And then also one should rescale the spectral parameter by epsilon u. And this R matrix goes back to the R matrix I introduced in this here. Okay. And this SU3 integrable spin chain model is well known as integrable, and algebraic variance has been applied successfully. So our strategy is that let's consider generic Q deformation theory and apply algebraic variance and take this limit, strong twist limit, and see whether we can see the really eigenvectors. Because according to algebraic variance, one can construct the one eigenvector per one eigenvalue. So one can find that the older eigenvectors. So that's why our approach. And then let me go through briefly what is algebraic variance. So based on this R matrix, one constructed so-called monodromy matrix, which is acting on auxiliary space, and each element of this monodromy matrix is acting on quantum space as an operator. And the trace of this monodromy matrix in auxiliary space is a transfer matrix. And then this fundamental commutation relation is obtained from the Yang-Basto equation. So I can find the commutation, sensible commutations between all these operators. Here is well defined, and then one can find the following result. So this eigenvalue of transfer matrix can be obtained by certain number of beta roots, where this UN is a first set of the beta roots, and then V is a second level beta roots, and so on. Because this is the beta ansatz, nested beta ansatz way construction. And here U plus means nothing but U plus 1. And then this becomes eigenvalue, and this U and then V, which are beta roots, are determined by the following sets of the beta ansatz equations. So this U satisfies between U and V, and so on. By solving this and inserting into that, one can find out this the eigenvalue, and by construction, eigenvector can be obtained, at least formally, because eigenvectors are obtained by acting this M12 and M13 and its combinations onto pseudo vacuum. So unfortunately, one cannot solve this kind of beta ansatz equation analytically. Numerically, one can solve, but it's very difficult to solve analytically. And so in principle, you cannot find eigenvalue in closed form, but one can solve in principle, and then it is solvable in that sense. Now, let's take the limit, this strong twist limit. First of all, let's consider beta ansatz equations instead of the beta vector. I'll address this beta vector later, but let's consider this. And if I take this limit, then this two sets of beta ansatz equation contains this epsilon factor in addition to this size. And then since epsilon is very small, or even actually goes to 0, one can find out the explicitly this beta roots, which is the following form. So these beta roots corresponding to, first of all, this first of all, number of U's there are actually the m number of the beta roots, and since I said that the capital K is number of these pi 3 fields, it turns out that this beta roots U, which there are m number of beta roots, but they are actually separated into two classes. One is that n small index n is 1 to m1, where m1 is m minus k, which is number of the pi 2. Then these beta roots are actually scaled into certain non-trivial factor times epsilon to the alpha, where alpha is so far undecided exponent. And then the other k remaining beta roots of U is actually scales like this -1 plus certain power of epsilon, and this is a non-trivial factor. And then second level of beta roots, there are k number of the nested beta roots here, and this vk is scaled by this, where one introduce another this exponent gamma. So there are 3 undecided exponent and 3 undecided coefficients. And inserting this ansatz into the beta ansatz equation, we found exactly the solution. And the alpha is given by this number, which is a rational number, and beta is also other rational number, and the gamma. And also, in addition to that, one can find this coefficient exactly in terms of Cauchy and then some root of unity, because in this beta solution, it's natural to have many solutions given in terms of certain roots of unity. So this W is given by L minus M1 root of unity, where M1 is M minus K. And then this index, the power, integer power of NK is given any integer set between 1 and L minus M1. Okay. So for a given set of this NK, since there are capital K number of W's, one choose some K different integers among this list to find out corresponding eigenvalues. Same for UN. UN, there are this M1 number. So there are bunches of these factors where W is given before. And this WL, which is L's root of unity with the power IN. And IN is integer power in the list between 1 and L. So choose M1 number of integer sets from this list to find the corresponding beta roots, and then insert into the eigenvalue formula. And this is how I obtain. Yes, yes.
So can you go back to the slide? Yes. So you make an ansatz to solve the beta equation. So
yes,
does
right.
this ansatz give part of the solution or give like all the solutions in that limit? Is it complete?
Well, we don't have a mathematical proof, but as you see from the strange features here, since we are taking epsilon goes to 0,
yeah.
Okay, this epsilon powers on both sides should match.
Yes.
So this restriction is actually very strong. So even though we don't have any mathematical proof that this is the only solution, we are pretty sure that any other variation cannot satisfy these conditions.
Okay.
Yeah.
Okay. And also here, just looking at this equation, if I have L equals 3K and epsilon, that power
yeah,
is
that's
0.
very interesting. Yeah. So actually you're right that if you consider L to be 3K and M equal 2K and K is K, then you notice that this epsilon factor disappears.
Yes.
So this goes back to usual finite Q beta ansatz equation. Only difference is that QK is replaced by epsilon K. So this is a very exceptional situation. And the solution for that is, of course, is the same as solution of ordinary beta ansatz equations. which we can solve analytically. So our solution does not apply to that special case.
I see.
So as you see that if you impose that condition here, then you will notice that alpha is 0, right?
Yeah.
3k minus 2k minus k is 0. And this solution does not make sense because we are assuming that alpha and beta and gamma should be positive because we are looking for epsilon expansion. So that possibility is excluded from this type of solutions.
I see. So from the spin train point of view, this choice of magnons and lengths seems to be special.
Right. That's right.
Because you cannot take that limit cannot be simplified in the limit.
That's right. And also it seems that in this limit, though beta centrifugation level they disappear, okay, for that special case, it does not disappear in the energy value. So if you say this is a finite beta centrifugation, eigenvalue and the beta centrifugation, and if you take this strong twist limit, in that special case, this epsilon disappears from the beta centrifugation, but it does not disappear from energy, the eigenvalue. And if you take that limit, then this eigenvalue becomes trivial.
I see.
You can see that easily because for example, this one survives, right? Q2k and n minus k is k, so they are somehow finite.
Yeah.
But this already incorrect because m minus k and l minus m cannot be same, and so on. So I don't remember, but this vanishes in epsilon goes to 0 limit. But this one, this one is also okay. This one is surviving. Yeah, okay. This one survives. But anyway, some epsilon dependence certainly enters into TU. So this is different from finite twist spin chain.
I see. So it's still simplified a bit.
Yeah, that's right.
Is there any physical understanding why this happens? What's so special about these values?
Yeah, so probably. So this means that this number of the three fields are all same. So pi1, number of pi1, pi2, pi3 are all same. And
so there's some additional symmetry.
Well, this renaming of fields is always symmetry, and also it's all possible permutation. So I cannot say intuitively why this is special, why beta centrifugation is independent of epsilon. But this appears only in the special combinations of Q's in beta ansatz level. So it's not obvious from the beta ansatz. I mean, why epsilon dependence disappears from the beginning.
Okay, thank you.
Good. Then it turns out after solving this beta ansatz equation explicitly and inserting into it, then one finds out that indeed the eigenvalue becomes L's root of unity, where this power of the root of unity, L's root of unity, is given by these numbers. Okay, and remember this nk is the arbitrary choice of the list between 1 and L minus M1. So one can choose a k number of integers, and then the same for I, so on. So basically, they generate all possible eigenvalues, although many of them are degenerate because it's basically L's root of unity. So eigenvalues are only L different values, but they are degenerate, right? So it is a natural, it's a consistent with my numerical diagonalization that the diagonal element is all root of unity, and for example, there are the 5 L minus 1 times L minus 2 over 2 eigenvalues, and this seems consistent with this. And then for example, let's consider so-called cyclic state. Cyclic state is the case where eigenvalue is 1. Okay, let's call it a cyclic state. Then if eigenvalue is 1, then this integer power n should be either 0 mod L. So we can find out that how many such degeneracy can occur. So one can simply calculate it. So since M1 is M minus K and the K is K, so for a given LMK, one can find the number of the possible configurations, which becomes 0 mod L, so that eigenvalue is 1. And interestingly, this is related to some famous mathematics problems called the Pauli accounting. So Pauli accounting theory is following that how many inequivalent necklaces can be made out of the total L beads with several different colors. So my case is that the 3 colors necklace with total L number of beads, and how many necklaces one can find. And well, naive guess is that since if I consider L, for example, red total number of beads is L, and let's call that there are K blue bead and L minus K red bead and L minus M black bead. Okay, and then since the possible combinatorics is that by this combinatorial factor, and then it's natural that they are repeating. They are, same number appears for each case because one can rotate each unit by 1. So I should divide by L, which is this. And actually this is why I call that this. Let me show you here. So I said that the size of the number of the eigenvalue 1 should be given by this number. Okay, this is already the M equal 3 case of this L minus 1 factorial divided by L minus M factorial K factorial, which is a 6. 6 means that it is 30 divided by 5, for example. But actually, it's not true. So the Polya instead constructed the so-called generating function for, say, if I reduce that to 3 colors, then is given by this generating function, where this pi over n is Euler pi function, and then this generating function, and then if I Taylor expand this logarithm, and then if I call the exponent of x is L minus M, which is a black, and then the exponent of y is a red, and the exponent of z to be blue, then this generating function generates number of the cyclic states given by LMK. So it is not actually this. And also this kind of a generating function appears in the context of the one-loop partition function of M4 superhangman theory. And this is the result. So if I use this naive counting, it's just divide by L, and for various different values of the LMK, then most of them are correct, actually. Naive counting is correct, most of them. But here I listed the non-trivial case where this naive counting is wrong, and different from Pauli accountings. Okay. But as I said, one can find out there's another way of finding this number of the cyclic state by considering from the beta answer solution. So eigenvalues. So since this is eigenvalue, I want to count number of solutions where this exponent becomes zero mod error for a given LMK. And using Mathematica, it's not difficult to find the number of them. And this is the result. For the case where naive count is not working, and all higher values of LMK, this fabulously, very interestingly matching. So this limit epsilon goes to zero limit is reproducing eigenvalues correctly.
One question.
Mm-hmm.
So, why are you interested in the cyclic dates? I mean, you want to find,
no,
yeah.
I'm not. Just
Okay.
for example, one can find, for example, eigenvalue omega L, which means that this n should be 1 mod L, for example.
Mm-hmm.
And then one can try to solve them. And the point is that this number of the eigenvalues with the omega L will be different from the number of the eigenvalues with eigenvalue 1 in this special case, where Polya the counting becomes non-trivial.
Ah, I see. Okay, thanks.
Okay. So this proves that this epsilon goes to zero limit of beta anticipation is working very well. Then the eigenvectors. Then we found a problem here. So for example, let's consider user eigenbeta algebraic variance method. So here I call B, but this is either M12 or M13. This is first level of creation operator, which is acting on some pseudo vacuum. Okay, and there are capital M number of beta roots, where these U's are beta roots, which I showed before, which satisfy the beta answer equation. With then since there are two the creation operators, one can introduce certain coefficients, because in principle all the linear combinations of this M different the M different operator B operators are possible. Okay. And then the second level in nested procedure is how to diagonalize these F coefficients, which is actually the main idea is nothing but SU2 cases. And SU2, one can also diagonalize using the algebraic variance. So this F can be obtained by SU2 level creation operators, which contains this second level beta roots. And they satisfy beta answer equation, which I showed before. Okay. Now, let me take the epsilon goes zero limit for these beta vectors. Here is very complicated, so we cooked up some graphical method. So this each horizontal line represent either M13 or M12. So M13 is that right point is 1, state 1, and the left auxiliary space has a state 3, etc., which I denoted by red line. And then 2 is I denoted by blue line, etc. So any combinations of this M12 or M13 acting on pseudo vacuum, then the top state is a corresponding beta vectors. Here, all the internal lines will be very complicated, depends on all possible the R matrix combinations. But if I take a strong twist limit over this R matrix to here, as I showed before, then there are among these possible the Boltzmann weights, which describe each vertices in this two-dimensional square lattice, it is reduced to very simple factors, depending on whether it is a U-type beta roots or the first type of U roots or second type U roots, depending on that, and with a certain factor of epsilons. Okay, I don't want to go to real details. And then one construct that the leading configuration of epsilon is ordered like that the first set of beta roots appearing the first, and so on, and then second k beta roots should appear in the later, acting on this pseudo vacuum, and then others are suppressed by higher order of epsilon, and then these beta roots are actually all boils down to the following, that for all beta solutions. So this U and the V are all solutions of beta ansatz equations, but any such a value of V and U, which I showed before, U and V is given here, right? UN is given by this second type, beta U roots are given by this with a certain exponents, etc., and its coefficient given explicitly here. So for any such solutions, these beta vectors all boil down to one vector, which is we call locked state, where all 2 appears first and 3 appears later, and then if I mark the first 2 as nth point, then it is summation from 1 to L. So in cyclic case, of course, eigenvalue 1 case, if eigenvalue becomes omega L, then I should multiply here omega L to the n. If eigenvalue is omega L square, then the coefficient is omega L square to the n, etc. But just for simplicity, I consider only cyclic state, and this eigenvector, this beta vectors, independent of the explicit solutions of the beta ansatz equations, all boil down to one vector. So this is a problem in the sense that we cannot find out all the eigenvectors, because at least for each Jordan block cell, because I showed that the Jordan blocks with the eigenvalue 1 is split into certain different of Jordan block cells. And for each Jordan block cell, there should be one true eigenvector, but beta ansatz equation generates only one trivial eigenvectors and no more. So this is the source of the problem. And although I explained the eigenvalues and the related Fourier counting, etc., successfully in this epsilon goes general limit, but still eigenvector, no. So we want to go further, but actually we have the limitation of numerical calculations. So we started to consider a little bit more simplified case. I mean, more, but the further simplified case where we named it as a hyper-eclectic model, is that there are 3 parameters, right? Cauchy 1, Cauchy 2, Cauchy 3, but let the first 2 parameters to be 0 and third one to be arbitrary number, non-zero, okay, say 1. Then Hamiltonian is given by this simple one, and this integrable. Okay, so remember this one is a 3 by 3 matrix where 1, 2 element is 1 and all other elements are 0, but it is acting on nth quantum space, and this one acts on n plus 1 quantum space. So this is a kind of nearest neighbor interaction. And then let's consider k equal 1 for simplicity. So k is, remember, number of 3 fields, type 3. So here I denoted by 3. And then m is a number of 2 and 3. So there are m minus 1 number of 2s. So since I'm considering only cyclic state, for simplicity, just it is a linear combinations of these sets, these states, where 3 provides some kind of reference point. So if the location of 3 is an nth location from the starting, this is 1, 2, 3, etc., up to n, where n is sum of 1 to L, then let's make a short notation this to be just this configuration. Of course, this final one is using cyclic property. This remaining one should appear here, called this state. And then interesting point is of this Hamiltonian is actually this is a translation operator. So this state 2, 1 goes to 1, 2. In other words, 2 is moving to right, but it cannot move to left. So this by acting Hamiltonian, state 2 always move into right by 1 unit until it meets 3. 3 does not move because there is no Hamiltonian acting on 3 space. So 3 is not moving, but 2 can switch the position with 1 only into the right direction. Okay, so if I act H many times, then say 3 times, it can move this first 2, 3 steps, or it can move the second 2 to 3 steps, or it can move this first 2 by 1 step and the second 2 as a 2 step, or all other possible combinations. Okay. Then Hamiltonian can be obtained very simply using this kind of a vector. And then I can construct a Hamiltonian from, say, for a given LMK, K1 here, but LNM. And then instead of the naively diagonalizing transform matrix numerically, I can use some better way using some mathematical formula, where this, according to this mathematical formula, let's consider some matrix H with eigenvalue lambda. Then as before, let's construct some matrix A, which is H minus lambda to identity. This means that they eliminate diagonal element to be 0. And then this A will have certainly some kind of the null state. And then according to this mathematical formula, the number of Jordan blocks with the size n is given by rank of A to the power n plus 1. So it's the matrix multiplication of n plus 1 times of this matrix A, and consider rank. Rank means that number of the non-trivial row vectors. And same for n minus 1 and minus 2 an. And they generate number of Jordan blocks of size n. Of course, this kind of calculation can be done only when one construct this A or H explicitly, which can be used mathematically to construct. And this is the result for some higher value of L. So first, let's consider still m equal 4 and k equal 1. So there are 3 pi 2 fields and 1 pi 3, and then there are many pi 1 fields. And this L equal 6 case, which is I showed before. And then it turns out that as L increases, the size of Jordan blocks, what I call Jordan block structure or spectrum, becomes very non-trivial. I claim that Y7 should be obtained. Let me show before my conjecture here that for L to be for m equals 3, this m equals 3, by the way, but it's given by this kind of formula. But m equals 4, the situation is much more complicated, and we cannot find any simple formula, some experimental formula for this m equals 4 case. Instead here, I exponented some exponent, and this means that 2 7 by 7 Jordan blocks appear. And then if I increase further, then even the number of the 24 side by 24 Jordan blocks appear 3 times, etc. This result is based on this formula. M equals 5, this is even further interesting, that it generates even this multiplicity increases a lot, and well, it's difficult to find some experimental rule. So the remaining question is that since we don't we find only diagonal elements, which is root of unity, but we still don't know why this eigenvalue, the eigenvalues of one cyclic state, for example, is split into this kind of Jordan blocks. One by one Jordan blocks, 5 by 5, 7 by 7, 9 by 9, 13 by 13, split into Jordan blocks. As L increases, even further non-trivial. This is all Jordan blocks with diagonal elements to be 1, for example. So to understand this a little bit, we have not succeeded completely, is that to observe the following, that let's consider this hyper-eclectic model where only state 2 moves into right. Then if I consider the configuration where the first state is all 1, and then the remaining one is all 2, and then 3 is just the final state. Then if I act Hamiltonian, it should move only 2 against 1, but after 2, there is no state 1 here. So it's natural that if I act Hamiltonian here, it's 0. So this is a true eigenvectors. Then one can consider certain, say, Jordan we call highest weight state, that instead of the 2 on the most right, let's consider 2 on the all left, and the remaining state is all 1. Then there are plenty of rooms where 2 can move. This first 2 can move until it meets 3, or other 2s also successfully can move. So if we call this a highest weight state, then one can act Hamiltonian until all 2s move against all these remaining ones until it becomes these true eigenvectors. Then if I act Hamiltonian one more time, then it becomes 0. So there are n plus 1 kind of Jordan block structure, which is exactly the reproducing this Jordan block structure, which I explained a little bit on the here. Okay, so from E1 to En, and then E1 is true eigenvector, and En is this Jordan highest weight. Ryo, can I have about 5 more minutes?
Yeah, okay. Yeah.
Yeah. So in this way, one can count what should be n to reach this state. So it is very simple that at each n, at each action of h, 2 moves 1 step. So for this first 2 reach before 3, it should move L minus m times, right? And then second one reach to the 3, another L minus m. So this since number of 2s are m minus 1, all this m minus 1 number of 2 state can reach in front of 3 to become this true eigenvector is simply m minus 1 times L minus m. So the Jordan block size should be this number plus 1, because this is just until it becomes E1. Then if I act H one more time, it vanishes. So Jordan block should be m plus 1. And this explains the largest size of Jordan blocks in each cases, 13, 17, and so on. This is exactly corresponding to that formula. Okay, here also 7, 19, 31, etc. So the first one is simple, but there are even more Jordan blocks, and how to explain those sizes is the question. And here, well, this is still we are in preparation, and it's not completed yet, but I'm just sketching how to obtain those Jordan block spectrum more qualitatively. So if I act H repeatedly, then this so-called I introduce distance to true eigenvector. So how many H should act on that state to reach the true eigenvector so I define the distance. And then there are if I act H and more, then distance decreases, right? From say N, which is the configuration of highest weight state, right? So this state has a largest distance to this eigenvector, true eigenvector. So as I act more and H on this highest weight state, it gets closer to this true eigenvector. So the distance should be from N, which is the case of this highest weight state, or 0, which is the true eigenvector. Then question is how to find out number of configurations with a fixed distance L. And this is a rather combinatorial calculations. And then this determines the dimension of the vector space for that configuration with a given distance L. And in that dimension of Jordan vectors, it can be either new highest weight state, which is corresponding to some smaller Jordan blocks, or the Jordan descendants of the previous highest weight state. And by computing this dimension of this distance of L for a fixed dimension, one can explain all these Jordan block structures using that formula. And then we are considering also generalize this to the higher K value of K, which is also working well. And then it turns out that it seems it's possible that we can extend this procedure to explain Jordan block spectrum for arbitrary LMK in hypercollective model, where only one value of epsilons. And if we keep all three coupling constant non-zero as a generic, for which we call eclectic model, then still we don't have any big clue, but we are a little bit have some progress recently, and we are preparing.
Question here.
Yes.
So you can explain now the dimension of the Jordan blocks. Can you also explain the multiplicity?
Yeah, everything.
Everything. Okay, great.
Everything here. It's not only the size, but how many such a given size is appearing.
Okay, nice.
Good. So let me quickly summarize what I said. So there are certain integral models which are integrable in the sense that there are infinite number of conserved quantities, but not Bethe solvable. And some of them is belong to this example where actually it's not Bethe solvable because it develops so-called Jordan blocks, which does not give all the eigenvectors, but only one for each Jordan blocks. And we try to understand that at least on eigenvalues based on this continuation epsilon goes to zero limit of known algebraic variants. But unfortunately, eigenvectors are all collapsing into, all becomes degenerate into one eigenvector, trivial eigenvector. And so we cannot construct all the true eigenvectors belong to Jordan blocks. At least there should be one true eigenvector for each Jordan block, but we cannot generate them. But by using this method, actually, we can find the Jordan block spectrum, at least, for certain limit of so-called hypercollective models. Okay, so main message of my talk is that strongly twisted supermix theory is not simple as it is originally considered. it is integrable, but even conformal dimension cannot be computed. So because it's not bit tensorable. So this Jordan block structure is it should provide some new challenge to the integrability. Thank you for your attention.
Yeah, thank you very much. Is there a question from the audience?
Maybe I ask one final question. So these spin trains are integrable. So what about the higher conserved charges? Have it been investigated?
Yeah, that one can construct, since one can construct the transfer matrix explicitly, you can construct the conserved charges as a u t of transfer matrix t of u, so you can construct the u expansion to construct the charges.
So they also like form Jordan blocks. So if you try to diagonalize them.
Yeah, that's a good question. It's actually actually it's very interesting question whether, for example, one may consider that the many of the charges are repeating, for example, right? Or maybe one need not diagonalize these charges. Sorry. Yeah, sorry. Since the transfer matrix generates the Jordan block structure, if you expand, then of course the quantum charges are also similarly non-diagonalizable. It generates Jordan blocks, and also the possibility which I raised that maybe charges are not all independent is a little bit inconsistent from the common sense that when you expand this transfer matrix in U expansion, then the charges are getting more non-local, like from nearest neighbor, then the next nearest neighbor, and so on. So I cannot believe that the conserved charges are repeating as the powers of U increases. So so in this logic, still number of conserved charges are infinite, and it's integrable. But ordinary algebraic variance is not working.
I see. Thanks.
Yeah.
Can I ask a question?
Yes.
Yeah. Hello, Professor Ahn.
Hi, Mingyu.
I remember 5 years ago, maybe Cayetano Kazakov
Yes.
studied some spectrum for this Fishnet strong twisted. So, but they, in my memory, they found some spectrum and wrapping correction. So is it related to your Jordan block structure or not?
So they considered the conformal dimensions?
Oh yeah, I think, yeah, for some 1 Magnon, 2 Magnon operator.
Yeah, then that's
I will type the archive number in chatting. Maybe yeah, we will discuss later.
Yeah, maybe we can, but I cannot comment on that. But yeah, if they claim that the best way to find this eigenvalue, the conformal dimension, is solving the spin chains, right? And in this maybe they consider some different sector that I don't know. We are considering here SU3 sector. Maybe SU2 sector, SU2 there is no Jordan blocks.
I see. Maybe That will be the SU2 sector. Okay.
Yeah, SU2 sector, no
That's
problem. There is no Jordan blocks.
Okay.
Okay.
Actually, I have some questions. The first question is, if you take this usual beta and wave functions before you take the limit, but if you carefully take this epsilon goes to 0 limit and then try to compute the difference of wave functions, do you think can you get this Jordan block descendants?
Yeah, actually, yeah. So yes, we also kind of consider that possibility. But well, you see that let's consider, say, two eigenvectors, okay, psi1 of epsilon and psi2 of epsilon, and then in this in the leading order of epsilon goes general limit, these two vectors become same, but sub-leading terms can be different, of course. Okay, then one can naively consider the difference of these two vectors and then normalize by some epsilon factors, such that you obtain, say, psi1 minus psi2 divided by certain powers of epsilon to be finite. Okay, are you with me?
Yeah, yes.
Yeah, then consider whether this is eigenvector, but it cannot be eigenvector because this difference is eigenvector of 0 always, because transfer matrix acting psi1 has a certain eigenvalue times psi1, and then acting T on psi2, then same eigenvalue with psi2, right?
Yeah.
And then you deduct. Then this generates the this does not generate the eigenvector of these desired eigenvalues. So this way you cannot construct.
I see. The second question is, since you have degeneracy, can you extend the algebra like a Yang SU3 by adding something like Jordan block descendant generator and then try to extend the algebraic structure, or it doesn't work like this?
Yeah, I'm sure that there exists that. And as I said, I called some intentionally all this highest weight state of these Jordan blocks because I think the structure is very similar as the usual conformal structure. So but we don't easily notice that structure yet. But I think there are some non-trivial mathematical structure in there.
I see. The last question is related to Minkyu's question. Since you have wave functions, I mean, the eigenvalue is the same, but the wave function is different, then probably you can distinguish different Jordan block states by computing 3-point functions, 4-point functions, overlapping corrections. But do you think is there any way like this to distinguish different states in different
eigenvalues differently, but one can identify. But the main problem which we have is that we don't know what is a wave function.
Yeah.
So there is no the eigen operator of the dilatation operators.
Except numerically, that's what you mean.
No, even numerically. I mean, we can find only in principle one should find out. Sorry. You are right. Sorry. You're right. You're right. That yeah, not through the beta ansatz. Yes. Numerically, yes, of course.
Yeah. Okay. Sorry. Yeah, that's it. Any other questions? Then let's thank the speaker again.
Okay, thank you for attention.